Yeah, just 1 minute maybe it will
Okay, okay.
require.
Right, right, right.
I have start because see, I don't start in the beginning because it.
Yeah, yeah. It's informal in the beginning.
Okay.
Done?
Yes.
Okay, so I'll start because Alwali sir is not there, so I'll take your permission to start.
Yes, please go.
Yeah. So, good evening, everyone. As we commemorate the International Year of Quantum Science and Technology, I would like to extend a warm welcome to everyone attending this special lecture series on teaching quantum mechanics and PER studies, including new paradigms and emerging trends in quantum technology, hosted by IAPT Regional Council 23 Himachal Pradesh. It's my great pleasure to welcome you all to this concluding day of the enlightening webinar. Over the past sessions, we have shared ideas, explored new perspectives, and strengthened our academic bonds. Today, we bring this journey to close with two remarkable talks by stalwarts of quantum physics and distinguished figures. We are deeply honored to have with us our National President of IAPT, Professor P.K. Aluwalia, will join in a moment, and our esteemed senior professors, Professor Ajay Gutta ji and Professor P.C. Deshmukh ji. On behalf of IAPT, I extend a very warm and respectful welcome to all of you. Your presence and insights are a privilege for us. I would like to offer my heartfelt greeting to our IAPT General Secretary, Professor Rekha Godpade, whose dedication and exceptional administrative skills have made gatherings like this possible. She will be chairing today's session also. So it's truly an honor to have you with us, ma'am. A special welcome to Professor Kuldeep Kumar Sharma, President RC23, along with all other dignitaries and valued participants who have joined us together today. Your presence adds immense value to this event. I'm sure today's session will be inspiring as they are enriching. So thank you for joining. And now I would like to invite Professor Kuldeep Sharma, President RC23, to say a few words. Over to you, Professor Kuldeep.
Thank you, ma'am. Good evening to all. On behalf of IAPT RC23, I extend warm welcome to all of you, and I welcome you to lecture 5 and 6 and to the last session of IAPT monthly webinar series on teaching quantum mechanics and PER studies, which is being organized by IAPT RC23 in July and August 2025 as a part of celebrating International Year of Quantum Science and Technology. During this lecture series, we had very interesting and informative talks by different eminent physicists from India and abroad as well. On July 28, Professor Dean Jolman, uh, University Distinguished Professor Emeritus Kansas State University, delivered a very nice talk on using interactive visualizations uh, to engage students in learning quantum physics. Then on August 4, we had another very important talk, one by Professor Chandra Lekha Singh, Distinguished Professor of Physics, University of Petersburg, on preparing students for second quantum revolution using research-based learning approaches. And there was another talk on the same day by Professor Gaske Waspis, Professor of Chair, Physics Education, Dresden University of Technology. And on August 9, we had very important talk by Professor Brian Lane, University of North Florida, on uh, highlights from investigating and improving quantum education through research. In today's last session of this series, I extend our warm welcome to our two eminent physicists, Professor P.K. Aluwalia, President IAPT, and Professor P.C. Deshmukh, who will be delivering expert lectures number 5 and 6 today. And Professor P.K. Aluwalia ji, will deliver expert talk on IAPT's Mega Quantum Quiz, Lessons in Engaging for Awareness. And last lecture will be delivered by eminent physicist Professor P.C. Deshmukhji, CA Most IIT Tirupati and ISER Tirupati. We are very honored to have both of you today with us as expert speakers of this session. I also extend our heartfelt welcome to Professor Rekha Gorpade, General Secretary IAPT, who will be the chairperson of today's session. Most importantly, I welcome from core of my heart our colleagues, Dr. Sapna Sharma, General Secretary IAPT RC23, Dr. Sapna Verma, our executive members, and all our respected IAPT members and all respected teachers and students to this last session of IAPT monthly webinar. We all have enjoyed the previous talks, and today also we are definitely going to witness a very interesting session with our two eminent speakers. I once again, on behalf of RC23, again welcome all to this session. Thank you. Jai Hind.
Thank you, sir.
Okay, so thank you very much, Kuldeep sir. Let's start our session. And before we start our session, there is slightly a change. First, we are going to have a talk by Professor P.C. Deshmukhji, and then we'll have it from Professor P.K. Ahluwalia. So let me give you the brief introduction of Ma'am Rekha Gorpade, as she is going to chair the session today. Professor Rekha Gorpade is currently serving as the General Secretary of Indian Association of Physics Teacher. Previously, she served as the head of the Department of Physics at RJ College, Ghatkopar, Mumbai, where she inspired generation of students through her teaching, mentorship, and dedication to academic excellence. Beyond her institutional responsibilities, Professor Rekha Gorpade has made outstanding contributions to the national physics education movement. She has served as the IAPT National Coordinator for the National Competition of Innovative Experiment in Physics. She has also represented India as scientific observer at the International Physics Olympiad, accompanying and supporting our national delegation in 2016. She blends administrative excellence with the deep passion for advancing physics education. We are truly honored to have Professor Rekha Gorpade with us today, chairing our sessions and lending her invaluable guidance to this gathering. So thank you very much, ma'am, for joining us, and over to you now.
Thank you. Thank you so much. Thank you, Sapna. So, respected speaker, Dr. P.C. Deshmukhji, Honorable Ajay Ghatak sir, Dr. Kuldeep Kumar Sharma ji, Sapna Verma, Sapna Sharma, other office bearers, and wonderful participants who are almost all the IAPT members. I feel really happy to chair this particular session. I'm thankful to RC23, and let me congratulate RC23 for taking lead in conducting these lectures as the to commemorate the IYQ 2025 movement. IAPT has, of course, started this IYQ 2025 movement in the month of January, and we have started the monthly webinars, and various RCs have come forward to host those webinars. And here is RC23, relatively very new RC. I think just 2 years back, this RC was born. And in 2 years, the RC has really done a commendable work. And I'm sure the credit goes to all the office bearers, Dr. Kuldeep Sharma ji, Dr. Sapna, Dr. Sapna Verma and Sapna Sharma, and the other coordinates. And of course, they are all guided by our able leader, who is the president of IAPT, Professor Ahluwalia ji. So congratulations once again, and thank you. And I'm sure that other RCs are going to, emulate all your the journey through which you have come up to this particular level. So thanks a lot. So today we have the sessions. I think it is a concluding session, though we have already completed the four sessions earlier. And now the fifth session will be conducted or be delivered by Professor P.C. Deshmukh ji. We all know that Professor P.C. Deshmukh by now because he is the one who is really guiding us in this IYQ 2025 movement that IPT has started. And it's an honor to have Professor Deshmukh with us as a IPT member and as a mentor also in many of the programs. For those, because now many of us know him and his books also probably because IPT actually has, I mean, on the platform of IPT, his books were released. One was on quantum mechanics and one was on classical mechanics. Classical mechanics earlier in 2022, sorry, 2019 at Allahabad Convention, and then the quantum mechanics at the Jaipur Convention. Currently, he serves as a founder or convener and mentor at the Center for Atomic, Molecular and Optical Sciences and Technologies, which is called as CHEMOST in Tirupati. So CHEMOST is a joint initiative of Indian Institute of Technology Tirupati and the Indian Institute of Science, Education and Research Tirupati, ISER. Co-currently, he is RV Chair Professor at the Center for Quantum Science and Technology, School of Computer Science and Engineering at RV University, where he guides research and educational efforts in quantum science, drawing on his vast expertise to support the center's growth and innovation. Besides, he is a Chief Technology Advisor to Vivekananda Institute of Professional Studies. And actually, if I just keep talking about PC Deshmukh sir, it will be 1 hour. So let me not, come in between. And I very extend a very warm welcome to Professor Deshmukh. And please start. Today he is going to talk, can we teach quantum mechanics intuitively in a uh, easier way. So I'm very eager to know because quantum mechanics, when you say quantum mechanics, many of the teachers itself, forget about students, feel very I mean, it is difficult to deliver to the students, and therefore we are eager to hear Professor Deshmukh on this particular topic. Therefore, so I invite Professor Deshmukh once again a warm welcome, and please come forward and start your session, sir. Thank you so much for gracing the occasion.
Thank you. Thank you very much, Rekha ji. I don't know about God or anything, but if there is one, I hope he or she will excuse you for your exaggerations. Your introduction was overly
No.
generous. But let me see if I can share my presentation, so that I can begin the talk. Are you able to see the screen?
Yes, sir. Yes, sir.
Yes, sir.
Okay,
Yes,
so
sir.
let me. All right, so the title of the talk is If Quantum Mechanics Can Be Taught in an Intuitively Appealing Way, Yes or No? And if I had seen this title of a talk, I would have guessed that the speaker will begin with the title, say no, and end his talk. So it should surprise you that I actually have the next slide. And the next slide is primarily to thank RC23 for the wonderful opportunity I have. Himachal Pradesh is a region very close to my heart. Let me tell you why. Means I spent some time at IIT Mandi, and here are This is the logo of the Indian Institute of Technology in Mandi. And these are some pictures from the time I spent at IIT Mandi in the first two formative years of the institute. I was on deputation and we had some great time at IIT Mandi. This is not the present campus, but it was in a temporary campus in the town of Mandi, just through the highway. And you'll see in this picture Sanjay Majumdar, who had come for a meeting, Steve Manson, who had also come for a meeting. Steve used to visit me at IIT Madras earlier, but he quickly found out that my students are much smarter than me. So we started moving the meeting to their basis. So here you have Hari, who had hosted the meeting, Hari Varma, and then you have Samiji, Ankur, Sindhu, Arti, Ashish also over here. So great times in the Himachal. Devabhumi, we are concerned about the rains and floods and landslides in Mandi. So I hope all of you are safe. Now, let me begin this talk with this article which came out about 10 days ago in Nature. And this is from the editorial of this issue, and in this editorial, it is written that everyone agrees that the mathematical framework of quantum mechanics is peerless at predicting the uh, all the results of experiments exploring the subatomic world. Moreover, it can be used to build technology ranging from computer chips to lasers and nuclear clocks. But what the theory means physically remains a mystery. And this is what poses a challenge to quantum mechanics. There are four questions which can be asked. Does this situation upset us? Does it embarrass us? And two more questions. Should it upset us? And should it embarrass us? I think more importantly, it is these four questions which almost drive us crazy as physics teachers. And my talk will be focused on handling these four questions. In the same article, it is said that some scientists are embarrassed that 100 years after quantum theory was first formulated, embarrassed by this inability to agree on a single narrative about the basic nature of reality. But the article also concludes that they shouldn't be. And this is going to be the main theme that I'm going to carry in this talk. The article concludes by saying that physicists should revel in the diversity of thought that the field represents and seize on philosophical disagreements as a way to spur further discoveries. So these are some of the ideas which I will propagate in this talk in my own very small way. And I begin by a very famous quote, which each one of you knows, but I really want to begin with Feynman, because I'm going to conclude also by alluding to this quotation. And that will be at the very end of my talk. And Feynman says that I can safely say that nobody understands quantum mechanics. And this is one reason why all of us are so worried. That not only us, but even stalwarts like Feynman have concerns so deep that they go as far as saying that nobody understands quantum mechanics. Then we have Niels Bohr, who said that anyone who is not shocked by quantum theory has not understood it. It doesn't mean that anyone who is shocked by quantum theory has understood it. That is my counter to this. And then David Mermin says that if I were to force up on in one sentence what the Copenhagen interpretation says to me, it would be shut up and calculate. And I would like to argue that this is not just a rhetoric. There is a deep sense when someone like David Mermin says it. These are some of the points that I would like to discuss in today's talk. Now, all this is governed by our presumption. And most of us teachers begin with the ansatz. We make an assumption in our mind that classical physics is intuitive, quantum physics isn't, and therefore teaching it in an intuitively appealing manner is simply impossible. I would like to begin by challenging this assumption. Do we understand Coulomb's law intuitively? Now, this is completely classical. And Coulomb's law is that two charges interact and the interaction energy goes as 1 over distance. The force goes as 1 over distance square. And it's not just the Coulomb's law, the gravitational law also has the same form. And I'm going to challenge the assumption that this part of classical physics, whether it is the Coulomb's law or the gravitational potential interaction law, do we really understand it intuitively? And the only way we can understand the Coulomb-Gauss law in Maxwell's equations, and all this is completely a part of classical physics, is by employing the Dirac delta function. And I have no idea how many of us would have found it to be intuitive. Now, Dirac saw that it must be true, and this is from the introduction to Fourier analysis and generalized functions by Lighthead, which is a very famous source for this, which is a very well-known, respected source. And then George Temple showed how simple it could be. And we have become used to using the Dirac delta function, not only in understanding the gravitational potential or the Coulomb law, but also many other things in quantum mechanics, but also in classical physics. And I'm specifically referring to those phenomena in classical physics where this is of great importance. Do we understand the Faraday lens law intuitively? This is again classical physics. Now, if you look at this experiment, and this figure is from my book on classical mechanics, if you look at this experiment, you have got a circuit here in which you have got a magnetic field which is orthogonal to the screen going into the paper. And if you move this wire toward the right or left, we know that a current flows. But we also know that if we do not move the wire at all, but move the field, so this is the field which you move toward the left, and then again the current flows. And we can ask the question, why does this happen? And for this experiment, you must invoke the Lorentz force law, whereas for this experiment, you must invoke the relationship between the electric and the magnetic field. And this is really very strange. And we don't even realize how strange it is till we read Feynman once again. And Feynman says in his book that no other place in physics where such a simple and accurate general principle requires for its real understanding an analysis in terms of two different phenomena. And the emphasis, of course, is on the word real understanding. It is very subtle. Unless you are an Einstein, I don't think this would be intuitive. And the first person to recognize this intuitively was Einstein, who recognized that it is important to come to terms with the fact that the speed of light is the same in every inertial frame of reference. And if the speed of light is the same, speed being distance over time, then distance must be different and time would be different. And he was able to get an insight into Lorentz contraction and time dilation. This is classical physics. And if it is intuitive, you need the mind of Einstein. For most of us, it is not. Let me ask a simpler question. Do we even understand what is speed? Speed is delta S by delta T in the limit delta T going to 0. And you can talk about 0 in very many ways. And I'll just pick on one of those and ask if 0 given by the limit 1 over n as n goes to infinity. Do we really understand these limits? Do we understand the infinitesimal? Do we really understand the infinity? That it is something and you can add something to it and it is again infinite. You again add something to it, it is again infinite. Do we understand it? Do we understand it intuitively? And our claim that classical physics is intuitive is based on all these things, which are all from classical physics. Yet, we are so much troubled by the fact that quantum mechanics cannot be taught in an intuitive manner, and classical physics is. And I'm challenging this assumption because there are a large number of concepts which are involved even in classical physics, whether it is electrodynamics, gravitational theory, or even elementary ideas of speed and acceleration. So I need to get into what exactly mathematics does to build our intuition. And I would like to quote, let me see if I can move this. Yeah. This is field medalist William Thurston. And he says that mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. Now, Thurston made a tremendous contribution to low-dimensional topology, one of the greatest mathematicians of recent times. We lost him a little more than a decade ago. Let me now ask, what exactly is intuition? And this is often described as the inner whisper. It is shaped by past experiences, subtle cues, subconscious processing. It is developed over time. It is reflective. It is just some sort of a feeling that you get without looking for any rigorous evidence. It can become deeper than that, and it is sometimes confused by what is often described as an instinct, which is like a primal reaction. It is almost biologically wired into our existence. It is hard coded in our survival system. It is automatic, like instinctively you pull your hand over a hot stove. So These are the ideas which determine our instincts and intuition. And the question is, can we build these? Now, these are deeply psychological, philosophical, intellectual issues. You need to carry out investigation into how knowledge is comprehended. And one of the very early analysis of this was by Sigmund Freud, who pointed out that knowledge can only be attained through intellectual manipulation of carefully made observations. Intuition is also described as perception via the unconscious. An intuitive person acts not using rational judgment, but by the sheer intensity of perception. And it is made up of fast decisions without comparing options. That, okay, is there an alternative? You don't need to get into that without comparing all these options. There is a recognition prime decision which you arrive at, and intuition is built on that. It has also been described as processes and thoughts that are devoid of typical logic, and as the ability to automatically generate solutions without long logical arguments or evidence. Now, to build intuition, whether it is to understand quantum mechanics or even classical mechanics, means different people have different levels of intuition. Einstein, Dirac fall in one category. Most of us fall in a different category. I would hope that some of you are in the former category, but I do not know. In any case, intuition, even to understand classical physics, has to be built. And there are a lot of intelligent people who are far more intelligent than many of us, if not all, who have not studied physics, who have not studied mathematics, who will find it very difficult to understand the Dirac delta function just because they have not had the training, not because they do not have the intelligence, but because they do not have the training. And I believe that this is where our opportunity as physicists comes in. Means we are here on this platform as physics teachers. We have undergone a certain training, and this training has to mean something which should give us a different handle on understanding deep concepts in physics, whether they have to do with the Dirac delta or the gravitational potential or the Coulomb potential or the special theory of relativity, or for the matter, the general theory of relativity, and even quantum mechanics. So our approach to this question must be different. And we stumbled with this idea that, okay, we do not quite understand what zero is because we do not know what infinity is, and we do not know what infinitesimal is. We do not understand these limits. Yet, if you look at the gravitational potential, you make a plot of either the gravitational potential or the Coulomb potential, and you plot 1 over r as a distance as a function of r. Most of us will be very comfortable with this without worrying about whether or not we understand infinity. But we understand this graph. We are very comfortable with this graph. And the reason is we have allowed our training as physicists to understand what is 1 over d, how 1 over d changes with d. We are very comfortable with it, and we would not be surprised by such a question if it is possible to teach the Coulomb's law in an intuitively appealing manner. We would jump to the conclusion that yes, what's the big deal? Now, do we really have an intuitive idea about this? And I don't know what the answer is, because I think we still struggle with the idea of infinity. What does 1 over r as a function of r look like as r goes to infinity? And we just don't know, because there is a point beyond the infinity and another point beyond it and beyond infinity. So this is very tricky. And let me quote von Neumann. He says that in mathematics, you don't always understand things, you get used to them. And we have become used to using infinity. We have become used to using infinitesimal. We have become used to using delta s by delta t in the limit delta t going to 0. And that leads to an understanding, which makes us very comfortable. And this is the power of mathematics. And it is this power which has helped us understand and teach classical physics in an intuitive manner. Yet, we do not use this power of mathematics to teach and use quantum mechanics in an intuitive, appealing manner, because we are stuck on quoting Feynman again and again and again, perhaps number of times n going to infinity, without knowing what infinity is, that nobody understands quantum mechanics. We learn from experience. And because of this experience we have in understanding delta s by delta t in the limit delta t going to 0, there is nothing intuitive about it. It needed Newton and Leibniz to come to this. For most people, it is not intuitive. It needed the intuition of Newton and Leibniz to invent calculus, to invent what is a function, what is a continuous function, how does it change from one point to the next, and can you describe this as a limit of a function from the left, from the right, which is equal to the value of the function, and then you take the difference at neighboring points, which are infinitesimally small, divided by the interval in the limit, the denominator goes to 0, becomes infinitesimally small. It needs the intuition of Newton. And I think if we were not taught this, most of us would not have ever understood it. But we have learned to use it from experience. We get used to it. Now, if we can get used to 1 over distance, can we get used to the Schrodinger equation? And here again, we know that most of the principles in quantum mechanics, as Feynman says once again, are contained in the heart of quantum mechanics, which is the Young's double slit experiment. And here you have got the grandmaster Niels Bohr explaining the Young's double slit experiment. And this experiment can be accounted for in terms of a state function which evolves over time, and its evolution from time t1 to t2 in the limit t2 minus t1, which is delta t going to 0, is given by delta psi And delta psi by delta t in the limit delta t going to 0 is given by this equation. The calculus is exactly the same as you have in the calculus which defines speed. Nothing different, absolutely nothing different. And if you use this, you're essentially talking about the time evolution of the state of a system. And then it takes just a few steps, which I will not go through. These equations from 1.87 and 1.91, there are just 4 or 5 equations in 1 or 2 pages, very simple mathematics, absolutely nothing challenging about it. And you can arrive at the Schrodinger equation, the time-dependent Schrodinger equation, and go ahead and solve it like any other differential equation with appropriate initial conditions, boundary conditions, and so on, depending on the situation you're dealing with. Now, what it explains are very bizarre things. Here you see the Young's double slit experiment. But on this single slide, I have this experiment at many different levels. You can do a which way experiment. And a which way experiment allows you to spy on the apparatus and ask, has the electron gone from slit 1 or from slit 2? And if you perform such a which way experiment, the interference is lost. Now, this is what makes quantum mechanics bizarre. The interference is lost. So the which way information destroys the interference, the which way detection. Now, if you lose information from this which way detection by using a quantum eraser, by putting a lens which will combine these two rays and bring them to a focus, and at the focus you do not know whether the ray has come from slit 1 or from slit 2, then the interference is restored. This is so bizarre. Now, what kind of intuition can explain this? But the Schrodinger equation explains it perfectly. Or what is even more bizarre is that if you put this lens far away, move it, if you see the cursor, move it to the left and go farther away, not just by tens of centimeters, but by millions of light years, it will still act exactly the same way. So this is so bizarre. This is one of the reasons that Feynman would say that nobody understands quantum mechanics. But don't forget that it is quantum mechanics which explains this in a very simple manner, because all that is happening, no matter how spooky it looks like, the simple thing that is happening, that when you have a which way measurement, the Hilbert space is expanded and the state vectors m1 and m2 are orthogonal, and the system collapses into an eigenstate from a state of superposition. It makes it so simple. You can keep saying that, okay, it is intuitively bizarre, but the explanation is extremely simple. It is as bizarre as infinity, but using delta S by delta T is so simple. Here is another very bizarre experiment. This is the Young's double slit experiment, and I'm coming to the end of my talk. But it is more complicated. There is not just a single slit, but more slits. You can have 2 slits or 3 slits or even 10 and more, or even millions of slits with 1 hole, 2 holes, 3 holes, number of slits, many slits. And there are infinite paths for this particle to go through. And it can get bounced off over here, get bounced off from the Andromeda galaxy or from Mars or anywhere. And you must sum over the paths. Now, this is the Feynman formulation of path integrals. And it tells you that all of this is accounted by this very simple expression that the state of a system is a superposition of various possibilities. The probabilities are given by the modulus square of these complex coefficients. And this simple thing explains just about everything in nature. It explains many other things. And one of the fundamental questions which was debated hotly between Einstein and Niels Bohr, and the debate started in the late 1920s, in the very early years of quantum mechanics, and I'm referring to the 1927 Solvay debate. And Einstein worried if the probabilistic nature in quantum mechanics had its origin in the same way in which there are phenomena in classical physics as well, which are probabilistic, like the toss of a coin. When you toss a coin, it can land on head or tail. And there are two options. And there are different pairs of two options that I'm comparing in this figure over here. And I have discussed this in a talk given on the IIPT platform earlier, so I will not go through the details, but I will just remind you of that here are three games in which the captains are different. Smriti Mandana, Rohit Sharma, and my favorite captain, Mahendra Singh Dhoni. And we look at the correlations between the results of the coin of the toss. And the results of these could be the same for Rohit Sharma and Smriti Mandana, or they could be different. And it could also be the same or different for Dhoni and Rohit Sharma. Now, if you compare these probabilities, which are just 50-50, then you arrive at an inequality, which is known as the Bell's inequality. And this is the great contribution of John Bell, that he provided a method of resolving between Bohr's viewpoint and Einstein's viewpoint by answering this question by referring to experiments that you can do in your lab. And these are the great experiments for which the 2022 Nobel Prize was awarded, Alan Aspect, and so on. The conclusion was that quantum theory is either non-counterfactual or non-local. And it was based on simple inequalities, which are as easy as understand if the number 9 is greater than or equal to 4 multiplied by 2. It's as simple as that. It also helps you understand quantum entanglement, because that is the very basis of quantum computing. And it tells you how to address this question. You worry if quantum entanglement between two particles, which can be separated by millions of light years, they could be in different galaxies. And these are the Bell states that you talk about. There can be more complicated Bell states or Bell-like states in multipartite quantum systems. And now you know that people are actually building quantum computers with a large number of qubits. There is nothing spooky about it, because it is governed by a simple fact that you have got the state vector of the composite system, which cannot be written as the tensor product of the factor states. And it is this which I like to call as reality 2.0, in which our conventional interpretation of locality breaks down. So that really brings me almost to the conclusion of this talk by quoting Feynman once again that quantum mechanics describes nature as absurd from the point of view of common sense, yet it fully agrees with experiment. So now, what is common sense? And Voltaire described common sense. He's pointed out that common sense is not so common. So the question is, as serious students of physics, what can we do to build this uncommon common sense? We are trained to understand and interpret derivative of a function. We are trained to develop an intuitive idea of 1 over distance. And we need to use the same training to accept mathematics as a tool to understand quantum mechanics. So now, this is my last slide, in which I conclude once again by asking you to answer this question. Can quantum mechanics be taught in an intuitively appealing way? Yes or no? And I would say that the answer is a superposition of yes and no. And it is a which way choice that you can make. Each one of you can make this choice. You have to free your choice from, if you force your intuition to be guided only by F equal to ma, then of course, this superposition will collapse into an eigenstate, which is no. But if you free your choice and allow your intuition to use the mathematics of quantum mechanics, which is very simple, it is no different from what you have used in F equal to ma. It is just a differential equation. It is only a second order differential equation. Then your answer would be different. And I will end my talk by saying that I can safely say that nobody understands nature, but many understand quantum mechanics. Thank you very much.
Sir,
Hello?
it was a wonderful understanding, a widely based understanding of intuitively appealing. Sir, I have a question here. You are
May I
saying
stop
that
sharing
if
my screen? It will be easier for me.
here itself in this slide, you are saying, will
Yes.
you free your intuition from F is equal to ma? Is
Yeah.
it possible? Because what we learned in classical or even quantum mechanics, that this is the basic equation where we start. Even the Schrodinger equation is based on that. So how
No,
able to
I don't
free
understand
yourself?
how Schrodinger equation is based on that.
Sir, when you talk about the equation, when you want to have you just collect the forces. Like from the force, you get the potential,
Mhm.
right? So one needs to know what are the forces whenever we want to formulate the equation. If I'm,
No,
please correct me if I'm wrong.
that is not the starting point, Rekhaji. The
Okay.
starting point in F equal to ma is the description of the state of a system. I know Professor Ghosh has raised a hand. I will come to you, Professor Ghosh. Let me
Yeah.
take a couple of minutes in responding to Rekhaji first. The basic question in mechanics, Rekhaji, is how do you describe the state of a system and how does the system change with time? And our earlier, older answer to this question was that the state of a
Mm.
system is described by its position and momentum. It is a point in the phase space. And how it changes with time, if Q is the position and P the momentum, then how these change with time, which are the Hamilton's equations, and Newton's equation F equal to ma is completely equivalent to that. So I don't have to refer to it separately, or the Lagrange's equation for that matter. It's all the same physics. In all of these three formulations, which is classical mechanics, the state of a system is represented by a point in phase space. You must know the position and momentum simultaneously and accurately. And how this changes with time. The first derivative of position with respect to time is its speed. The second derivative is the acceleration, and the acceleration is proportional to the stimulus F equal to ma. This is the ansatz of Newtonian mechanics. The ansatz of variational principle is different, but I can discuss it separately, but it will take more time, and I don't want to cut into Professor Ahluwalia's time. But the essential point is, it is this ansatz which is the starting point of classical mechanics. The starting point of quantum mechanics is different. That the state of the system is described by a wave function, and how it evolves with time is given by del psi by del t, which is the Schrodinger equation. The starting points are different. The mathematics is pretty much the same. There are some differences. There are different formulations, but they are equivalent. You can do matrix mechanics. There are many different formulations. You can do scattering theory. There are easily 9 different formulations of quantum mechanics, which are documented in the American Journal of Physics. So the starting points are different. And in as much as F equal to ma explains the Coulomb's law by taking the derivative of the potential and explaining to you what the force is, you use the same calculus. Your starting point is different. It is a wave function or a state vector. The wave function is nothing but the coordinate representation of a state vector. And its derivative is the Schrodinger equation. You go ahead, solve it. So this is what David Mermin says. Shut up and calculate. Okay, there is a deep reason for it. It's not just a rhetoric. Or when Feynman says that nobody understands quantum mechanics, it is not just a rhetoric. It is warning you that do not try to understand it in terms of what you knew from classical physics. Free your intuition from that. And if you do that, you can understand quantum mechanics. You may still not understand nature. And that is my concluding remark at the bottom of the slide, that I can safely say that nobody understands nature, but many understand quantum mechanics. Please understand it. Please use it. Please teach it with confidence and build this confidence amongst your students. Now, let me take Professor Ghosh's question. I'm not sure if Rekhaji is satisfied with the answer.
Thank you.
But,
Yes.
But we will continue
later.
Yes, we can continue to discuss and debate it later.
This later.
Yes, let me take Professor Ghosh's question.
No, I actually raised my hands to clap. It was a very interesting talk, Pranav. And yeah, it's very intuitive, and I completely agree with you that quantum mechanics can be taught in a very intuitive way. The question that one has to understand is, when you want to teach quantum mechanics, whether you want to teach it at an earlier stage of students' career, in which case does it become incumbent with the mathematical background, that how much of mathematics background, F equal to ma is much easier. But you actually say that there has to be, after all, a differential equation, which also means that the students will have to be aware and how to solve differential.
I totally agree, Arindam. I completely agree.
So
when you teach it, when you teach quantum mechanics after a course in electrodynamics and so on, students are led through using mathematics, and they start gaining confidence in it. So without that experience, it is certainly very difficult. And if you are to teach it at the high school level, where you do not have that experience, it is a challenge. And I would still recommend that it needs to be attempted, just because it has become the necessity of the day to introduce young minds to quantum mechanics. There is also a caution which goes with it, that, okay, do it very carefully and don't give hand waving arguments which can actually be misleading. For example, I have seen arguments such as people saying that, okay, the two slit experiment is like a coin which is spinning, and a spinning coin has neither a head nor a tail. It's not as simple as that. A spinning coil is a spinning coil. It is not the Young's double slit experiment. So don't make it too simple. And I would like to remind Einstein once again. Einstein said that, okay, everything should be made simple, but not too simple.
Sir, may I?
Yes.
Yeah, sir. Professor Ghosh, please go ahead.
Thank you very much for an excellent talk. It's always a pleasure listening to you. In fact, you removed the screen. I was enjoying this linear combination of answer.
Yeah. Yes.
Most interesting, innovative linear combination I've ever seen.
Yeah, it is a which way choice. If you choose not to free your choice, and insist that, no, I must understand it only in terms of what I understood from classical physics, then you will never understand it. In fact, I'm reminded of a discussion at the chat of an IAPT meeting. It was hosted by the Kerala Regional Council. And I casually said that you start understanding quantum mechanics when you stop making an attempt to understand it. And what I really meant is that you stop making an attempt to understand it in terms of what you knew from classical physics, not when you stop making an attempt to understand it. Of course, you have to make an attempt to understand it. But if you try to keep understanding it in terms of QP and F equal to MA, there's no chance.
So like delta T tending to 0, we are all tending to Feynman.
Yes.
I have two observations.
Absolutely.
Yes. I'll be very brief.
Yeah. I like to define that as an expert function who knows more and more about less and less. And in the limit, he knows everything about nothing.
Sir, two observations. I am also very much passionate about infinity, and like the questions you have raised about infinity. And it's quite interesting to note that we have spent quite some time on explaining infinity, the concept of infinity. And we have problem in explaining it to young students. Now,
yes.
If we can visualize infinity, I have two suggestions. That is, one way is to explain it by tan theta as theta going to 90 degrees. That is, you're approaching, suppose you're walking on a road and approaching a multi-storied building, and you're raising your head. And at some point of time, you'll have some complication like vertigo. So this is one way of feeling infinity. And
yes, the path to understanding, Professor Ghosh, the path to understanding nature is through mathematics.
Definitely.
And this is completely in line with what Wigner said, that how mathematics is used to understand nature. It is a wonderful gift we neither understand nor deserve. And our job is to use it to our advantage, to the advantage of our students, to the advantage of technology. We can understand semiconductors, lasers, quantum computing. All this is business. We have absolutely no business to challenge quantum mechanics.
And another way I try to approach to infinity, that is visualize infinity. I was talking about that.
Sure. One can do that.
If you go on increasing the number of sides of a regular polygon, We
Yes.
find that when the number of sides become infinity, how it becomes,
Yeah.
then we get a circle. And if we
True.
link this with the statement that you cannot draw a circle equal in area to a square, Ramanujan did it in a very,
Yes. Oh, yes,
then
absolutely.
it was an approximate, but still it was an approximate. And you can draw
Yes.
any regular polygon equal in area to any other regular polygon, provided the number of sides are finite. Once the number of sides become infinite, you cannot do that. And perhaps this has a subtle relation with the definition of a transcendental number like pi, that it cannot be obtained as the root of an equation with rational coefficients.
Yes,
Obtained
indeed.
as an equation. So, is there any subtle relation between these two? These I keep telling, perhaps without understanding much.
No,
And
no, I completely agree. These are very subtle issues and very fascinating, very challenging. I think we need a lot of time and a separate discussion for this. So we will discuss it later.
and if you
Professor
permit,
Sharma has a question, is it?
Yeah, Professor Sharma.
Sir, good evening, sir.
Namaste, good
Not,
evening.
they are not a question, sir, but comment that your talk is very wonderful, sir. The need of penetrating to understand the quantum mechanics through parallelly understanding the classical and introduction of the quantum mechanics through the mathematics, the basic fundamental understanding which we generate through the foundational aspects of mathematics is wonderful, and that is where we have to work as physics teachers to find out, to devise the methods how we can introduce these ideas at the initial level, at the school level, or the first year of the UG level, in which we can make this, we cannot make it counterintuitive, but somewhat acceptable,
Yes.
the ideas to make the student acceptable. But because as a student and as a teacher also, I have faced that whenever first time that the one person is interacted with the quantum mechanics, it is a total dilemma for him or her,
No,
that what is going on.
I would do it. I would do it in how quantum mechanics came into being in a historical manner.
Yeah,
And even means certainly one can go to the black body radiation,
sir.
but my favorite starting point is spectroscopy. Look at the spectrum of the hydrogen atom and try to interpret the frequencies of the of the emission lines, and then go to the formulae, the completely empirical formulae, the semi-empirical formulae developed by Balmer and Rydberg. And H, what we call as the Planck's constant, I like to call it as the Planck-Einstein-Bose constant.
Yeah.
But this is already there in the Rydberg constant.
Yeah.
And introduce it in a semi-empirical manner, and many of these things can be done at the high school level.
Yeah.
And
So
I think
your
that is the way to go. That is the way
yes,
to go.
your talk or the many coming talks are the actual guides through which we can delineate the path how to understand quantum mechanics at the school level. That
I
is the
hope so.
comment which I
I
wanted
hope
to.
so.
Yeah,
I think
Yes.
it needs to be done,
Sir,
but
we
it has to
have
be done very
some more
cautiously.
questions
thank you very much.
actually.
Yeah.
Yeah, thank you so much, sir. Before we go over to Professor Ahluwalia, he has raised hand for a long time. There is one question which I have received here on the personal thing. Can I ask Ahluwalia, sir? I will come to you little just.
please go ahead.
Yeah, this is Mr. R. Sujoy asking, sir, so is it the fact that escaping Newtonian reality, indeed from the realm of those thoughts, enlightens one with the counterfactual truth of a greater nature justified within the quantum realm? It's very complex statement.
Yeah, I know R. Sujay. He is a very bright
Yeah.
student. I work with him very
Okay.
closely.
Okay.
I would assume that
Great.
this is the same Sujay. His questions are often loaded. And Sujay, I suggest that we discuss it in person. He's here in Bangalore. We can meet. It is often loaded, but very often his language is also very heavy. So I think it needs some time to decipher his question and then
Understand.
answer it. But I will definitely do it, Sujay. Let's meet up and talk about it.
Yeah.
Because
So
otherwise,
we
we are not going to
will
have
would
Professor Aluwalia's talk this evening.
yeah,
It
we
will
have
be
one more
tomorrow
talk
evening.
by Professor Aluwalia. Before that, sir, please ask
Yeah,
your
thank you very much. Thank you very
your
much. In
comments.
fact, I was cursing myself that the first part of this talk I really missed. I got stuck in rain actually somewhere, and I
Oh,
had not
Yeah, I
carried
know
an umbrella.
Himachal is having
Yes.
heavy rains. I hope all of you are safe. I mean, that's
So sorry for that. But there were few thoughts coming to me after listening to your talk. It's always a pleasure to really listen to your very, very deep thoughts and the kind of understanding you have got for the subject. I think that's a blessing and a pleasure for us. I just want to say two things. One was that it was from my early college days when our mathematics teacher started teaching us limits and continuity. And he also started talking about infinity. So many many people were saying, "Sir, हमें समझ में नहीं आ रहा है infinity ये क्या होती है? आप क्या बोलते रहते हो ये infinity infinity?" उन्होंने कहा ऐसा करो ना, ऐसा एक मेरे पास एक सेब लेके आओ और मैं आप सबको एक एक सेब दूंगा। और उन्होंने ब्लैक बोर्ड पे एक एक्सप्रेशन लिखा, 1/0। He said, this expression says that this apple you have to give to as many people as you like, but make sure that you give that fellows who stands in the queue only 0 apple. And tell me how many people you can give that apple. So now you have the answer about infinity without knowing any definition about that infinity.
Yeah.
The second thought which was coming was from a talk which I heard long back. I think I heard it on the radio. That was in 70s. And this talk was given by Professor E.C.G. Sudarshan as a Nehru Memorial Lecture. And there he just at the end of his talk said one thing which is, I think, the most crucial thing in understanding these subjects like quantum mechanics, and that was abhyaseti anandeti. And he translated it into English. He said, practice is bliss. And I think it goes without saying that all these people like Feynman admits that, look, I have worked very hard on understanding things. It's not that they came to me like that. I was trying
Absolutely.
to do everything with my own hand, and that is how I got the understanding.
Yes.
These were the two thoughts which were coming. I thought I should share with the participants here. Rather, there was another thought which was coming. I think we should have such dialogues very often in IAPT platform. And the what you call this IT makes us really listen to wonderful lectures in a very nice way, intuitive way, I would say, without much paraphernalia around. So maybe we can think of even doing that, bringing some scholar, asking those questions, rather having a question answer session itself. So
Sure.
that was what I want to say. Thank you very much.
Thank you, sir.
Thank you, sir. Thank you very much. I think this kind of session, you don't feel like ending also because things are really emerging in a very positive way. And it's a learning thing for all of us. Thank you, Professor Deshmukh, for enlightening us. This was a really different perspective of intuitive approach for the quantum mechanics. We hope to interact more and more on different occasions on IAPT platforms, of course. So I wish to thank you all from on behalf of IAPT itself. And now I would like to move to the second session, right, Sapna? We can, yeah. So it's Professor P.K. Ahluwalia. Due to some technical difficulties, sir could not join. I think he just explained us, and then he's here to talk with us. Actually, it's not a lecture going to be, and Professor Aluwalia does not need any introduction because for last 4 years, I think all the entire IPT community is very well versed, well familiar with sir, and people know what sir has the contribution in physics education research area. He under his able leadership, entire IAPT across the country is really growing so very well academically, and thank you sir for that particular initiative. He's very passionate about the physics education and, of course, doing the um, various programs on various platforms. He is not only generating ideas, but he keeps following them and wants to materialize them also. This is one of the thing that he has coined here, the mega quiz, mega quantum quiz. I think this mega quantum quiz is a very innovative idea, and I must appreciate that conducting the 22 mega quizzes is not a very, I mean, it's really not common or very easy. And not only conducting quizzes or giving the answers or the response, but he's here to discuss the responses. I think this is really a wonderful session. We all are going to enjoy, and we are eager to hear from Professor Aluwalia regarding what lessons are we going to learn from this mega quantum case. So over to you, sir.
Thank you, ma'am.
I I can formally welcome you, though you are a head of the
Thank you.
family, but still,
Thank you.
on behalf of the participants here in the meeting, I would like to welcome you here for.
Thank you very much.
Yeah.
It's a pleasure to be in this uh, evening set of lectures. And I think we are having a wonderful time in IAPT these days. In the last 7 months, I think we could engage very effectively with our community and even beyond that. And I think our community has different, levels. We have students, we have teachers from schools, we have students from undergraduate colleges, we have teachers from undergraduate colleges, we have students from university departments, we have teachers from university departments, and many people who are not to say so-called physicists or immediately indulging in teaching or learning of physics are very passionate about physics. The idea of this quiz came way back in December when we started thinking about celebrating International Year of Quantum Mechanics. And then we thought that can we really engage with that community who may not have been coming to our lectures, but still we can catch them in one way or the other. And that is how this idea of mega quantum quiz happened. And we said we want to engage them not for, say, one quiz or two quizzes, but a series of quizzes based on the development of the quantum mechanics. When I say quantum mechanics, I also want to include before that when we were talking about old quantum theory, starting from 1900 till date. So it's a period of about 125 years. I think this period, because of physics, because of quantum mechanics, has changed the world, whether we realize it or not. And one of the aims of celebrating this year is that we should
bring awareness about quantum mechanics among the students, teachers, and general public also. So this was like a outreach program which we talked about. Now, only yesterday, the this series of quizzes ended, and we had, when we started in the month of March, from day one, we had about 22 quizzes. And fortunately, I had a wonderful team with me who really said, okay, we will work hard for it. And it was not, I would definitely say, an easy task. And it was also like that, that we were also not knowing many dimensions of the development of quantum mechanics. And on the way, I think we have also learned a lot. When I joined Professor Deshmukh's talk, uh, I heard this famous quote of Richard Feynman, which I have also thought I should put on the first slide of my talk. And it is once again that nobody understands quantum mechanics. And how far it is to be taken seriously when a person like Richard Feynman says that, I think there's a lot of reason for that. And he must have even got this from his own experience, that understanding quantum mechanics is not difficult. But for us, this was a passion kind of a thing that we said, okay, let us see whether we can really make people appreciate and understand what went on in quantum mechanics. So the outline of this talk is that I'll give a brief introduction, then I will talk about designing of this quiz, then I'll see that how we thought about engaging with community. You will also agree with me on one point, and that is keeping people with you for such a long 6-month period with this idea was itself a Herculean task. It was not easy. And then when we started doing it, we said, look, we are going to really get a lot of analytics out of it. And maybe that will also give us a lot of insights on very many aspects of teaching and learning of physics. I think it has just ended yesterday. It's a work in progress to look at those analytics, but a few things I would like to share in this particular presentation itself. So our aim was celebrating 100 years of quantum science and technology with the young minds. Our target audience was definitely young students. Bring more awareness and understanding about quantum mechanics. Talk about its relevance and connection with us as human beings. That's also very important, that when we are, say, studying this, learning this subject, seeing that how technologies have emerged from it, I think it's a very, very important task that we sometimes forget about, that what is the relevance of this particular development in the last 125 years for us in our daily lives also. We also wanted to make sure that this quiz is accessible and should be inclusive. So all these aspects we actually kept in mind. This was, in a way, a unique opportunity for a mega outreach for us in IAPT. And we were fully aware of the fact that when we are going to run this quiz, we are going to have a mixed audience. And that audience will be of very many, layers of people around us. And these two pie charts will tell you very easily that who were the people who mostly participated in it. You can very easily see that 50% of the share was taken by the undergraduate college students. And that means that the target audience, which could really appreciate and understand this, was with us. Then a lot of what you call university people, a quarter of that were participating in this workshop. So this number kept fluctuating. Every time we were getting this pie chart for schools, colleges, and universities. And also we were trying to see that how many undergraduate graduates are in it, how many enthusiasts in it, how many institutes are participating in it, and how many teachers are participating in it. So we were able to even have a view of that. And we had also asked a very specific question: are you a student, teacher, researcher, scientist, technologist? And you can see from this graph, this pie chart, that people with varied, tastes, they were all coming and trying to understand and appreciate it. I was very happy that a good number of, school teachers are also there in it. So I think, though in the beginning we were worried about the mixed audience, but that was a good way to proceed further, and it was a challenge for us also. And when we talk about awareness, I am reminded of a quote from Carl Sagan, who said that it will be a tragedy if people who use technologies these days or use science these days is not aware of how this science operates and how this technology emerges. And it is our duty that we should really do that kind of a task also. Even one of the constitutional values which we have is this, which is called scientific temper, which we see as a kind of a mean for bringing reformation in the society and make it a humanistic task itself. So what was the best part of this? And that was that when we sat down, we said, okay, we have to decide about the level of questions which we are going to really pose in these quizzes. And we know that we talk of different cognitive levels of the questions. Education people always talk about Bloom's taxonomy. So we decided that we are to target in this particular set of quizzes things which are at the level of knowledge, a bit of comprehension, and sometimes, with a series of questions touching upon the application level also. But most of the times we kept ourselves around knowledge and comprehension itself. And the idea to bring the purpose of this application level in these questions or in examples was that it will help audience see the relevance of quantum science and technology to their lives and making it more engaging and interesting for them. So focusing on knowledge, comprehension, and application levels also, made this possible that we could access a broader audience, including school students who may not have advanced knowledge of quantum mechanics. So we were daring to really talk about it with an audience about whom we wish to really see as the early, the students for quantum mechanics, so that they may walk into the quantum workforce and maybe get into the kinds of quantum technologies which we are talking about today. Also, we wanted to be very inclusive in the sense that we made sure that it's not just that a few people participate in it, but we made sure that we asked this question also when this quiz is going on, that how many male, female, or other, gender was there in this quiz itself. And one of the very interesting things which was happening in this quiz, though it was fluctuating, that female participants were sometimes more as compared to the male participants. And this is also something which we were targeting, and that was really good for us. So when we were really talking about designing of this quiz, we kept following basics in mind. And one was that quiz must cover major milestones of quantum science and technology, starting from 1900 till date. And we know that quantum mechanics has been winning Nobel Prizes after Nobel Prizes, and that series is continuing. And whenever we are talking about anything, particularly on quantum information and quantum entanglement, quantum computer, we are seeing that it is a very, very live kind of a subject and is not at all in any kind of a dormancy. Also, we wanted to focus on basic quantum concepts and experimental landmarks so that we are able to tell that when we are talking about quantum mechanics, people may call it very, very counterintuitive, but still it has a lot of evidence to bank upon and to believe in those kinds of counterintuitive ideas which quantum mechanics brings before us. So this is also very important. And then, we talked about quantum revolution 1, and we also talked about quantum revolution 2 in our journey of this mega quantum quiz. And to be very frank, the team also had lots of, learning on the way and the kind of unbelievable things which we came across while drafting these questions. So once it was done, we told the team, look, we will have to work in a very dedicated manner, and we have to run this quiz online every Saturday, and we must try to take a regular feedback to improve the engagement of the participants. Now, the main question was gathering resources to draft quiz questions. You can see that how big this task was. One was that we could have gathered these questions from, say, some textbooks, etc. We did not follow that kind of a path. We said we will go to the textbooks when the need will arise. Let us try to go to that kind of a literature where people talk about quantum mechanics and really remove that kind of a mystery out of that. Let us also talk about biographies of the quantum scientists and the stories of the development of quantum technologies. And we went to writings and popular articles written about quantum science and technology. We also banked upon online resources and many references which are quite easily available to us. One of the triggers actually came from a very interesting book which was shared by one of our friends, and that was on the journey of this quantum theory. And it was called Quantum Theory, a Crash Course by Bran Clegg. And I think that was a wonderful book which really gave us how we should really move ahead if we have to really conduct this quiz. Then there was another thing, that what kind of format we should have in conducting this quiz. We chose a format of multiple choice questions. In between, we were also tempted that, okay, let us ask some short questions, etc., etc. But we found that it will be very difficult to assess and evaluate, and let us follow a path in which, through multiple choice questions, let this task be taken over by the computer itself, and immediately we will get results and good analytics out of it also. We also followed what we call PER path to assure the quality of questions by prior validation of each question by the team through correctness of the stem, as well as the choices both scientifically and historically. Designing in the choices distractors to telling the participants attempt was also tried. Also, we saw that, in IAPT for the last 2-3 years, ever since I have been interacting more vigorously with our honorable members, there has been a lot of talk about cognitive levels. We conducted a workshop also of 2 weeks on training our teachers in identifying cognitive levels of questions, or when they draft questions, how to really aim for a particular cognitive level of knowledge, remembering, comprehension, understanding, and application, or such things. But it's like this: we give a quiz, people attempt it, after that, we forget about that for the whole week. We said we are not going to really do that. We will enhance engagement with the students or the participants, whosoever are there in this quiz. So we thought we should really create an e-booklet of the questions of each episode with answers, and also, bring some famous quotes of quantum scientists to, and we posted it in the WhatsApp group of the participants so that they immediately start, seeing not just statements of the question, but some, images posted with each question to, take their imagination further. Also, we were very sure that we should have feedback, as I mentioned earlier also. So we designed two feedback formats. One was mid-mega quiz feedback, and other was the end mega quiz feedback. So we made sure that I believe in one thing, that if you want to really know what is happening on the ground, feedback, feedback, and feedback is the mantra which we should really follow. Then we also, thought of having a proper format of the Google form, which should be not very complex, attractive. And apart from having those fixed number of questions, it also was decided that we will gather relevant information about the background of the participants in terms of parameters, which will help us gather analytics for the ease of further analysis, like male, female, school, college, university, student, teacher, researcher, technologist, physics enthusiast. So this was what we kept in mind. And this is how we, went ahead with the, taking this message to the community through our own website, through a WhatsApp channel of IAPT called IAPT at 40 plus. Through IAPT website, we also sent about 4,000 members whose emails are there with us this message that, look, we are going to conduct this very important program of quantum awareness and celebrating quantum mechanics 100 years. And we started on 14th of March 2025. Through various WhatsApp groups also the messages were sent. Participants registered through Google form, whose information was available. Mega quiz was administered through a dedicated WhatsApp group of participants. So every evening we will find that it will get posted. We were very particular that if we have committed that it should be there up at 7 o'clock. So it will be up there at 7 o'clock. So we are not going to really change that time also. Now, I would like to share with you now some sample of this quiz, and also about this quiz booklet which we prepared. In fact, this sample of the quiz has got analytics in it. And let me see if I can really show you. Try to see, this was that quiz. I hope you can see this here. And you are actually seeing at the moment questions. So they were put here, all these things were there. And then we started, engaging with the student with very simple questions. Like, for example, what was Max Planck's approach to physics? What problem did Planck solve by introducing the concept of packets of energy? What award did Planck receive in 1980 for his work on blackbody radiation? What personal tragedy did Planck experience during World War I? In what year did Max Planck die? Where was Niels Bohr born? With whom did Bohr work at Cambridge? What model of the atom did Bohr publish in 1913? So, slowly and steadily, what we did was we were mixing some physics something regarding the personal life of the quantum scientists, and also, talking about some numbers, talking about, giving some kind of a knowledge. And these were not very tricky questions, simple questions. Knowledge and comprehension focus was there. And this is how we went ahead with this format. This is a small sampling which I wanted to give to you regarding this uh, quiz itself. Now, after that, what we did was we also created a mega quantum quiz booklet. Now, here it is. I hope you can see this. And this is uh, drafted in Canva. So we started, bringing something in it. Who was the team who has done this work? That was also mentioned in it. And we also had a kind of a title for the quiz, that what we are actually doing in it, bringing more pictures with questions. These were, freely available. These were, available in Canva, in which these were drafted. Suddenly, you will find that the uh, the feel of the quiz changes the moment this booklet goes in the hands of the students. So small things, maybe who is the one who is doing the thing, what are the basic concepts which are involved in it. For example, we brought in electromagnetic wave theory, electromagnetic wave in vacuum, its speed. Then these images, were also there, thought in such a fashion that they should find some kind of a relationship in the question which is being posed. Very simple. Uh, and then, for example, look at this picture and try to see what was unusual about the photoelectric effect when it was discovered. Then uh, uh, this was, I think, a very meaningful engagement which we had with the participants, and we gave them the answers of the quiz also here. And then we brought in a quote. For example, in this, most of the times we were talking about photoelectric effect. We brought in a quote from Albert Einstein, which was a kind of a communication which he had in a letter to Max Born. Quantum mechanics is certainly very imposing, but an inner voice tells me that it is not yet real thing. The theory says a lot, but doesn't really bring us any closer to the secret of the old one. I, at any rate, am convinced that he, that is God, is not playing at dice. Now, look at the context in which this sentence was written by Albert Einstein to Max Born, and then how Max Born gave an interpretation to the meaning of the wave function and the probability in quantum mechanics itself. And again, we had the names of our team. We also had one student from NIT Hamirpur, Mr. Shashank Mishra, who really worked very closely with us. So this was that booklet which we really gave to the participants. Let me go back to the quiz now. So this is where we were. Now we started, talking about, after all, what is this quiz telling us? So there was a lot of data which was coming in terms of analytics, and some data which is given by Google form itself, if we design it properly, is one thing, mean score, which was basically seen as giving us a kind of a feeling of average awareness level. And it also indicated that higher mean score indicates a higher overall awareness level, while a lower mean score suggests a lower awareness level. Then mean score also tells us about the central tendency of the data, giving us an idea of where most participants stand in terms of awareness. Then mode actually tells us what is the most common score. And it appears, it is something which appears most frequently in the data set. and a high mode score might indicate that many participants have a good understanding of the topic, while a low mode score could suggest that many participants struggle with the material. Also, when we try to look at the responses, each question gives us wonderful analytics. In this particular talk, I'm not going to talk, and I think a lot of work needs to be done on that to appreciate and understand how people responded to each of the questions. And maybe that can help us bringing out some kind of more common misconceptions which need more education or clarification through these kinds of the programs itself. Then there is another thing which is there, which is called range of scores. This is also very easily available in the Google form. It tells us the variability of awareness. The range of scores indicate the spread or variability in awareness levels among participants. A long range might suggest that some participants are highly knowledgeable, while others struggle to understand the topic. And sometimes, we were also looking for, are there any outliers in it? For example, participants who scored extremely high or low compared to the rest of the outliers. This might help identify areas where additional support or education is needed. And, when we get these results, we need to really interpret these. So we went through, statistics books. We also went to Google. We also went to AI and tried to see what will it mean, because every distribution of scores which we're getting was different from what we were getting for the last, say, episode of the quiz. And these were the kinds of, insights which we were getting. And maybe it will help us to look forward in refining even our quiz or adjust it and even refine our educational material. There was one thing which I always thought that we are missing in this online quiz. Whenever an offline quiz is held, the quiz master brings very many interesting things for the participants who are sitting before him. And I wish if we could engage with elaboration of this e-booklet further as far as this aspect was concerned. Then there is another parameter which is there, another metric which is there, is the median. And it also tells us a kind of tendency that where is the middle value of the data set when it is arranged in order. And this indicates middle performance. The median score represents the middle value of the data set, separating the higher scoring half from the lower scoring half. Robustness to outliers. Unlike the mean, the median is less affected by extreme scores, providing a better representation of the total performance. And it also provides us an indication of the skewness in the data. If the median is significantly different from the mean, it might indicate skewness in the data. For example, if the median is higher than the mean, the data might be skewed to the left, that is negatively skewed. So we also tried to see from the median in quiz score, typical performance, comparison to mean, understanding score distribution also. Now, I'll show you an overview of this data, which I have actually created in a Word file. I hope you can see that our first quiz was general knowledge on quantum phenomena. There were 324 participants in it. We really kept number low. We were feeling that if number is kept high, maybe we will not be able to keep our audience with us. What was the average? You can see that 64.8% was the average score. Median was 70%. Range of marks was between 1 and 10. You can see in this distribution also. But you can also see the kind of mode which is reflected in these average and median values is there in this particular graph. When we went to the next quiz, which was focusing on what was happening before actually Planck came on the scene, we typically call that Victorian era of the physics itself. We found that the scores were not showing a typical, mode. We were able to see there were a few students or the participants with high score. There were students with a kind of a score which was not much different from here, but it was also telling us a story. Now, if you look at this, here you will find that there is a mode coming here and then there is a mode coming here. So the topics were in this quiz old quantum theory, Planck, Bohr, and Schrödinger. Photoelectric effect came in the fourth one, and you can see that more and more people were able to attempt this. And the percentage score really was 79.4%. 90% was the median. So here we found that this was the part which was, attempted by most of the people correctly. And maybe when you saw that pie chart where I was trying to show you that there were a good number of undergraduate students who were there in it from colleges, I think this behavior is being reflected in this particular chart itself. Then we had one dedicated to black body radiation puzzle. Here also you are finding that the level of awareness is very, very nice. And then we came to this concept of quanta, wave nature of light, energy frequency relationship, etc. Here also you can see that this was a reasonably good awareness level was visible to us here. Spectra and Bohr model, then beginning of quantum mechanics, that is matrix mechanics. Here again we found that there were very few people who scored less, but there was a good number and it was also a kind of a bimodal distribution here. Then we talked about Pauli's exclusion principle. We brought in quantum spin, and we also talked about emergence of relativistic quantum mechanics. Dirac was mostly here in this quiz. Subtle counterintuitive concepts of quantum mechanics like superposition, wave function collapse, measurement, coherence, interpretation of quantum mechanics. Very, few people talk about in journal, teaching of quantum mechanics. What are the various interpretations of quantum mechanics? Quantum technologies, entanglement, spooky action, Dirac's equation versus Schrödinger equation. And in this, you can see that number of questions also, was increased. But you also see how starting from the first quiz, we had 324 participants in that. But this number was actually decreasing. But fortunately, still there were 100 people who were there with us throughout the quiz. And I think that was a success which we could achieve by engaging more and more with the participants beyond just administering the quiz itself. In the next 13th quiz, we talked about zero-point energy and Feynman diagrams. Then we brought in quantum mechanics in daily life, tunneling, speed limit of information. Professor Deshmukh's talk also had a reference to this superluminal experiment, frustrated total internal reflection. Then we also focused one episode to the biographies of quantum pioneers and interpretations of the quantum mechanics itself. We also devoted good time on the Einstein's, Podolsky, Rosen paradox, and Copenhagen interpretations. We also brought in Bell's inequality. Try to see this distribution, it's a very interesting distribution. We would love to go into the details of that. There was another very interesting thing which I must mention here, and that was that we were finding that the Google Analytics also provided us with a set of questions which were attempted wrong by more than 50% of the participants. Those are very interesting indicators when we are looking at it. Then quantum teleportation in qubits, quantum computing, quantum Zeno effect, quantum revolution and some biographies, quantum technologies like superconductivity and optoelectronics, Bose-Einstein condensate and superfluids, quantum chromodynamics and quantum biology also. We even included these topics also in it. So this was all which we wanted to really look at. This was an overview which I have given to you. Now, we were really asking a few questions immediately after the when we were reaching the end of it. That let us try to see the distribution of participants and what was it telling us. And we found that the average is 135.18, median is 127, and maximum value, minimum value difference is 234. So the engagement is of moderate level if I have to really draw a conclusion. The median value is slightly lower than the average, suggesting that the distribution might be slightly skewed to the right. Range of 234, that means large range indicates a significant variation in participant numbers across episodes, with some episodes having much higher or lower participation than others. The distribution also suggests that participants' engagement varied significantly over the episodes, with some episodes having much higher participants than the others. Now, when we really look at it, we were also asking ourselves, what is the reason for this kind of a higher dropout rate? And one conclusion can be that some participants might have found the quiz too challenging, lost interest, or didn't see the value in continuing. Also, a reason can be lack of engagement with them, difficulty level, or maybe something wrong with the format also. We also try to see that what about if we want to look at participants' motivation. So maybe they started with enthusiasm, but lost motivation as the quiz progressed, leading to a decline in participation. Maybe we will have to think about how this quiz can be made more engaging. You know, when we were having feedback, we were finding that the participants were looking forward to some kind of quantitative questions to be asked in the quiz for providing more engagement. But that also then needed that we should have a longer duration for the quiz to run. Then we also were looking at quiz difficulty. Maybe that if the quiz is difficult, we don't know, say, about the history of the people, don't know about some subtle questions about quantum mechanics. This may also lead to frustration. There is another part also of this. If the quiz was too easy, participants might have lost interest due to lack of challenge also. Now, these are some of the questions which were coming to our mind. Maybe it has something to do with the target audience. Maybe some kind of initial learners of quantum mechanics would have benefited much more. Otherwise, it would have led to mismatch between expectations and reality. Also, you know, participant selections. Maybe that way was not the best way to select people. Maybe we should have really interacted more with the teachers in schools, colleges, and the universities at a more vigorous level so that these self-selected participants become sponsored by the college or the school or the university. One thing, what lesson which we have learned is that we need to reevaluate this quiz in terms of content, format, or difficulty level to better engage and retain participants. This is one of the lessons on which we must really think very seriously. The remaining 100 participants, you know, in the last almost 12 versions of this episodes of this quiz might represent a more dedicated or motivated group, which could provide valuable insights into what works well for this type of quiz. So maybe we need to really now see them in person in some kind of a interaction session online and see how we can get those kinds of insights from them. Also, we would like to see that those people who dropped out, we can also get to see that who are the people who dropped out. We can analyze how they were attempting their quiz. Can that gives us some kind of a meaning of the reason that this higher dropout rate was there? And these insights can help us refine our approach to creating engaging and effective quizzes. Now, let me come to just one quiz in detail before I think I'm very much close to the end of this, uh, presentation. I have picked up quiz 6 here. And in this quiz, you can see that the mean, that is average, median, and range were given by Google. I again calculated it by hand, that means in an Excel sheet, and I found that it was matching, and we had a average score of 68.33%. Median was 11, indicating that at least half of the participants scored 11 or higher. Mode was, it was a bimodal distribution. Mode was 10 and 11, and it suggests that the most common scores are 10 and 11. Distribution suggests that the population performed reasonably well in the quiz with moderate, mean, and median score. As far as this distribution was concerned, we didn't see that there were some extreme outliers, means somebody who has done very well or somebody who has done very low. And we find that the scores are relatively clustered around the mean and the median. But we must also remember that in the other distributions which I was sharing with you, the impact of mixed population from schools, colleges, and universities is there, and it is actually telling us about their performance. We need to dig out in the data once again, separate data for schools, colleges, and universities, and see that what story they are telling us. So it is work in progress. I think we enjoyed doing it, and our feedback, which we have got, that also really kept us dedicated and motivated to interact. There is a lot which we can get out of this task as far as its study using physics education research methodologies involved. I would love to hear your questions, and maybe I'll try to give answers if there will be with me, and maybe some comments. And this was, my team, I would say, our team, IAPT's team. Professor Kuldeep Sharma, he is here in this webinar. Sapna Sharma, who has really worked, both these Kuldeep and Sapna, they have worked very hard in curating this quiz. And, we were talking for more than 4 to 5 hours in a week to make sure that the quiz is properly validated. Dr. Ramurthy, treasurer RC23, was also with us in this task. And then, as I told you, one student of Professor Kuldeep Sharma was with us. I would like to end this with one quote once again. I think this is very, very relevant in the light of what we heard in the last talk also. Quantum mechanics makes absolutely no sense. Just live with it. You don't have to understand the nature of things in order to build cool devices. And I think that's all what I wanted to say. Thank you very much. And I will be back with you. Thank you.
Thank you, sir.
And
that was wonderful, Professor Aliwalia. I
Very much, sir.
congratulate you and your entire team. The
Thank
other
you.
names you mentioned. It's a tremendous effort. I really saw the tremendous amount of work that you do. So, the main conclusions, if you can just say once more, what are the main conclusions from this extensive tests that you have done?
The main conclusion is this, sir, that it is not that quantum mechanics is being seen as a subject which is that you don't need to touch and you should always feel scared. The participants' presence in the quiz showed us that there are people who can be engaged for meaningful learning of quantum mechanics. And I think we should really catch them and make them come and not make us in any way pessimistic about that physics and particularly quantum mechanics is very difficult to learn.
I talked to Vandana yesterday, Professor Vandana Luthra, yesterday after the seminar, and we were talking, and she mentioned that you are planning, that NCRT is planning in a big way to introduce quantum mechanics, not quantum mechanics, quantum theory and qubits and these things at the school level. So I was very happy to hear that. I said that that is very good, very nice. And so apparently, do you have any more information on that? And I'll just end there.
Sir, they have already made the teams. Professor Vandana is also part of the team, and I think it is good that IAPT has got representation in that particular team. It is good because in the last 2 years, sir, we also submitted our concerns to NCRT and to CBSC and to Ministry of Education, Government of India, that when you are drafting syllabi, these are our concerns on which you should really pay attention. And I think presence of our IAPT members in that group, we have Professor Vijay Singh in that, we have Professor Bhupati Chakravarti in that. So I think it's good that whatever we are thinking or talking about in our community, it will echo there when they will sit down and discuss about writing of the textbooks.
I see that Vandana has raised her hand.
Yes, sir. Yeah.
Yes, sir. A very nice talk, sir. And it is in fact indeed so nice to see all this. Sir, I have two queries in this case.
Please.
Sometimes when we are posting quizzes, and these are being posted, say, on offline or online, there is an influence of the technology, because when you type these quizzes in AI, any AI model, you get prompt responses. So sometimes one has to tune the timing of performance of these quizzes so that there is no influence of those things into it. That is one thing, because I having conducted many quizzes now, I have faced these challenges. And second thing, would it also be useful in case there are different quizzes for the different section of people, like when we are talking about UG students and the school students, or do you think that the same can be given to all?
Thank you very much. I think we were also worried about it, that maybe when we will post this quiz, people will go to the Google or maybe go to some chat bot and try to attempt it. Let me tell you that when you look at the results, outcomes, the attempts of the people, you find that in every quiz there were 3, 4, 5 such questions which were attempted by less than, say, 30% people. 70% people didn't really give the correct answer. So that showed that these kinds of technology interventions were not helping them with the quiz. Second thing is this, that we made sure that the timing for each quiz is decided by the number of questions which are there in that. And there was one column which I didn't really talk about, where if there were, say, 10 questions, we said we will give, say, at the most 12 minutes or 13 minutes for this quiz. After that, we will remove this quiz. So we made sure that happens. What was your second question you said regarding?
It was regarding different question sets for different set of
Once we have this question bank available with us, rejigging this question bank for reaching out to different audiences will not be difficult now. I mean, creating these questions was the toughest job.
That's right.
Validating these and seeing that, when we posted our first quiz, suddenly participants bombarded us with maybe that question is wrong or that question's answer is wrong. But then slowly and steadily, our persistence with the validity of the questions worked, and we didn't find that there will be many, such, aggressions on us also as quiz masters.
Yes, it is a huge task, and I must applaud the whole team for that. It is really, really a good resource also, and it can be used as a pedagogical tool also, because it has a sequential and a graded sorts of topics included into it. So I think, sir, congratulations to all of you.
Thank
I
you.
may only suggest that if you want to have a prompt response, one can also try online tools like Slido. In that, the questions can be asked can be asked in a very, very short time of say 10 minutes. And then there is no time of getting influenced by any other AI tool or otherwise. So that can also be one of the suggestion which can be taken into.
There is one thing, one reason that we created these e-booklets. They are a PDF booklet.
Yeah.
You
Yes.
can take each booklet, go in your classroom, and suddenly say, okay, come on, we are going to have a quiz. This is the time which I am going to give you. That's it. So that means that we have created a big resource,
Yes.
thanks to celebration of the 100 years of quantum mechanics, for
That's
the
right.
teachers to take in the classroom also.
Yes. Thank you so much. And again, my appreciation for the whole team. Thank you. Thank you, sir. Thanks a lot.
Thank you, Vandana.
So how do we get that
Professor
booklet?
Bush.
That we will share with you. Don't worry.
Is it on the book? Is it on the IAPT website?
As yet, sir, we have not posted it. What we were thinking was that now we will go to that IYQ international website. There we will create a post. In that we will give a link, and we will try to give this quiz as an international quiz.
Let us
So
know
that is
when
what
you do that.
that is what we are aiming at. But sir, for our teachers, we can always share the resources on a separate link so that they can go there on a Google Drive and download those booklets. That we can always do. So we will create that Google Drive, folder in which systematically all these quizzes will be put. Rather, we were thinking that we should check these again because we were, stressed by time also, so that if there are any corrections which are needed in that we will do. So thank you, ma'am.
Thank you, sir.
Sir,
Thank you.
sir,
Professor
I
Ghosh
also
is already there. I think
Professor Chinmoy is
Professor
also.
C.K. Ghosh is also has raised a hand. Sir,
Am I audible?
can you?
Yes.
Am I audible?
Yes, sir. Yes, sir. Yes, please go ahead.
Am I audible?
Yes, sir.
Yes, sir. You are audible.
Yes, Chinmay, you are audible.
First, I joined Professor Ghatak and Professor Luthra in complimenting Professor Ahluwalia and the entire team for this excellent initiative. In fact, we'll look forward to further developments in this area. Just one observation, Professor Ahluwalia mentioned about that in an offline quiz, when the question answer session goes on and the question may be answered by the participants, or maybe the question bounces back to the quiz master, and after telling the answer, he or she does not stop there. He elaborates on it and tells interesting fact about the questions. You have mentioned that. I don't know, when I am not that much technically sound like Professor Luthra or others, but something can be inbuilt in anticipation in the answer, so that related to the answer to a particular question, those information can be conveyed to the participants.
Actually, we were thinking about that, sir. But what was happening was that our e-booklet was really getting very, big in size, in number of pages. That okay, let us really try to engage with each question and then give this booklet. Maybe in the second version of this quiz, we might do that, sir. This is work in progress, as I said. We are not going to stop just here. I think this hard work must reach somebody.
Thank you. Thank you.
Okay, thank you, sir.
Thank
I
you,
also-
Professor Chinmay Ghosh. Yes.
Sapna. Ma'am, it's me, Sapna. Yes.
Yeah, Sapna Verma.
Yes, sir. Yes, ma'am. Sir, I also want to appreciate your teamwork in understanding this quantum mechanics. And I think that when teachers and students are not confident enough about the strangeness of quantum mechanics, and with the quote of Feynman that nobody understands quantum mechanics, I think beginners had an easy escape to get away from this branch of physics But such type of quizzes and awareness techniques is really giving all of us a good start, sir. Thanks to all your team. And we can come over with these frustrations and barriers and put some courage together to feel challenges of quantum mechanics. So this type of groundwork is really appreciable and making a difference in quantum mechanics concepts. And it's really creating a hope and meaningful learning to all of us. And again, a big, applause to all of us and all of you. Such a research work and intense work was done in framing these datas and analyzing these datas of quizzes, sir. Thank you. Thank you once again to your team, sir. To you, sir.
Thank you, Dr. Sapna. Thank you very much. Sapna, we are
Thank you,
inspired
Sapna.
by two very inspiring teachers who are with us in this session itself, Professor Ghatak and Professor Deshmukh.
Yes, sir.
That is what makes us feel that let us try to do, even if we can do 1/10 of what they have done. I think that will be a joy for us.
Definitely, sir. Definitely, sir.
Okay.
Yes.
I think this is really not only a mega quiz, but it was a mega task actually, because people do conduct quizzes, but giving such a wonderful analytics, which will really help in framing the quiz, is really going to be helpful to all of us. I'm sure those the team members who have really framed the questions and did the analytics. So for them, it must be a really learning experience.
Oh,
How
yes.
to have the questions using Bloom's taxonomy, and um, again doing the analysis of that, and how to not only the four options for multiple choice, but it is a really a difficult task to select the options and the distractors. Framing the distractors is more challenging than having a correct answer, because a correct answer is really easier, but framing distractor must be a really a challenge for all of you. I'm sure this is going to have a great repository for IPT, and it will be available for all the members very soon, and could be, as Sir has already said, that this is not only I mean, we are not ending here, but the process is going to go on. The work is in progress, and we wish the entire team of RC23, and of course, I'm sure I'm very hopeful that the other members from the other regional councils also will join this good event here. Thank you so much, Professor Aluwalia, for giving such a wonderful analytics, which was really an eye-opener, and which was really helpful to have how the quizzes can be formed. Thank you, Professor Ghatak, for adding the comments to it and enriching us. Professor C.N. Kumar, C.K. Ghosh, Professor Vandana Lufra, Professor P.C. Deshmukh also, and the team leading RC23, Dr. Kuldeep Kumar Sharma, Dr. Sapna Sharma, Dr. Sapna Verma, Dr. Hemant Kumar also must be here, yes, and the other members, of course, for continuing this, at least taking the initiative and continuing with the task. I wish the great success to this team for the entire event.
Thank you.
And finally, I hand over this platform to Professor Sapna Sharma for the concluding remarks. Thank you for giving me the opportunity to interact
Thank
with
you.
all of you.
Thank you.
Thank you.
Thank you, ma'am Rekha. Thank you for
Thank you, ma'am.
wonderful chairing the session. Thanks a lot. And thank you very much, Professor Aluwalia. Thank you very much, Professor P.C. Deshmukh. Both the talks were extraordinarily brilliant. Actually, I was totally engrossed and very interesting. Thank you, Vandana Luthra ma'am, for your suggestions. Ajay Ghatak sir, your presence and your suggestions also. P.C. Deshmukh sir, thank you very much for a wonderful talk about quantum mechanics as usual. Your talks are really very, very much interesting and beneficial to all of us. So
Just 1 second,
Really,
Sapna.
yes, ma'am.
One second. In the chat box, I have
Yes.
pasted the message from Professor Joshipura that
Oh, yeah.
RC7 is also organizing some online
Yeah.
event. I request participants to see that message. And I suppose Professor C.K. Ghosh has again raised the hand.
No, no, no.
Okay.
Yeah.
Oh, sorry. So you
Yes.
forgot to lower it down. Fine.
Oh,
It's
sorry.
Thank
it's
you.
RCO7 is organizing online event.
Gujarat.
Yeah, Gujarat. Professor Joshipura has said that. Yeah. So we have noted it down. So I think I would now like, finally the things are over. It was a learning experience. These 4 days were quite learning experience for me, and this mega quantum quiz was also a learning experience for all of us actually. Every Friday we used to sit and moderate the quiz, and Saturday we have to post the quiz. So it was such a thank you very much, Professor Aluwalia, for always supporting us.
It has been a
So
team effort. It was not one person's task. It's a big,
yeah,
big team effort.
yes, 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 yes. Of course, it was a teamwork, but behind that team, you were always there to encourage us. So that was possible because of that only. So
Yeah,
thank you very much.
certainly the team has done splendid work, and I am sure it is enabled by Professor Aluwalia's leadership.
Yes,
It's
yes,
amazing.
yes, yes, yes.
It's
Professor, it was
so
due to Professor
big
Aluwalia's push
hand,
only.
big
Yes,
hand to Professor
Thank you.
Aluwalia and
Thank
the
you
whole
very much,
team.
yes,
sir. Thank you.
yes, sir.
Yes,
Yes.
But still, I feel that it is teamwork, sir. If team is not there, then
it
work is
is.
not
Yeah,
done.
yeah, yeah. It is. It is. It
But we
certainly
need some
is.
motivator also. I mean,
Yes.
to do such a
A
big
source
job.
of
So
inspiration,
yes.
motivator, mentor. Yes.
Yes, so Professor Aluwalia was always there for us. So once again, thank you, sir. And finally, I would like to invite Professor Sapna Verma to deliver vote of thanks from on behalf of RC23.
Thank you, Sapna Sharma ma'am. Regards to everyone. I am Sapna Verma, Executive Member RC23. First of all, I would like to congratulate the team IAPT RC23 for completing a webinar series on celebrating International Year of Quantum Science and Technology 2025. The topic, Teaching Quantum Mechanics and PER Studies. It's my extreme pleasure to say this, as narrated by Dr. Rekha Godpade ma'am, because IAPT RC23 is a newly born organization around 2 years ago. And the way it is progressing with each coming time is remarkable. And with the able guidance and vision of our National President, IAPT, Professor P.K. Aluwalia, General Secretary Dr. Rekha Godpade, and stalwarts like Professor P.C. Deshmukh and many, many more. So my heartfelt thanks to whole IAPT national team to push us to the boundaries of perfection and encourage us to perform our duties in the field of making this, quantum mechanics understanding more interesting. So I want to take a moment to express my sincere appreciation and thanks to whole IAPT team. Thanks once again. Now I have an esteemed pleasure to thank today's eminent speakers, Professor P.C. Deshmukh, Professor P.K. Aluwalia, for putting over their self-perspectives in these two wonderful sessions, which are really thought-provoking and a feast to our minds and ears. So we truly express our gratitude for your presence and for enriching this event beyond our expectations. Professor P.C. Deshmukh sir, Rekha ma'am was not over exaggerating the things. She knew what type of a session is actually coming. So I extend my heartfelt gratitude to all IAPT senior professors, IAPT members, students who spared their valuable time and considered them as a part of this remarkable journey. A very special thanks to our international speakers and guests. It is always gratifying to see that how much we have gone through together and intellectually globally connected together. So on behalf of IAPT RC3, thanks, big thanks to all of you, stalwarts of the physics. Thank you very much.
Thank you,
Thank
Sapna.
you, madam. Thank you.
Thank you.
Okay, goodbye.